Okay, this is chapter 3, section 3, and what we're talking about is increasing and decreasing functions and something called the first derivative test. Now these are used for determining where a function is a local minimum or local maximum. So let us continue on here. So this is to remind me that yes, I know it's to remind me of. We talked about critical numbers in the first section, and we said critical numbers are possible values of x where the function is a minimum or a max. Well, actually, critical numbers are possible points where there's a minimum and maximum. And critical numbers are where the value of the derivative is equal to 0 or the derivative is undefined or does not exist. And here's a function, though, where if you take the first derivative of the function, you get that. And you ask what values of x is the first derivative equal to 0? Well, the answer is at x equals 0. So you might say, oh, well, we have a maximum or minimum at x equals 0. But if we draw this curve, which we should know from pre-calculus, it is a cubic, and it comes up like this, and then it goes through 0, and then it continues all like that. So we don't have any maximum or minimums, but the second derivative is equal to 0. The slope here goes to 0 and then becomes positive again. So we have to have some means of determining whether a function is a maximum or minimum at a critical point. In this case, we're increasing and then we continue it to increase. So the first derivative test looks at changes in the function from going from increasing to decreasing, or the other way, from decreasing to increasing. But let's talk about what increasing and decreasing mean. There's really two definitions. A function increases, as a function increases, the derivative is positive. So our example over here, if we draw tangent lines to this graph, you'll see that it's always a positive slope. It goes to 0 here, but it never becomes negative. So this is an increasing function for the entire domain, and the derivative is positive. The other way you can think of it is that the function increases as you go from left to right. It always is getting bigger or staying the same. It never gets smaller. In contrast, if we looked at the similar function, y equals negative x cubed, then the function would look like this, and it would go through 0, and it would go the opposite way. So this function is always decreasing because the slopes are always negative or 0. So the slopes of the tangent line. In this case, the function value is always getting more negative as x becomes positive. Now, it turns out the function changed from increasing to decreasing and vice versa at critical points. Now, just because it's a critical point doesn't mean it changes, but it does change when you have critical points. So here we are, the function is increasing, we have a positive slope, we go to 0 slope here, then we have a negative slope, it's decreasing, negative slope, 0 slope, and then we switch from negative slope to positive slope. So here we're increasing, here we're decreasing, here we're increasing. If I found the critical number for this function, I'd find that the critical numbers are at x equals whatever this value is and x equals whatever that value is. So what we're going to do is we're going to use the critical points to determine where we're going to look, and then we're going to look on either side, on the left-hand side or the right-hand side, and see if it changes from increasing to decreasing or from decreasing to increasing. If it does, then we know it's a maximum or minimum. If in contrast, if it goes from positive to 0 to positive, then that's not a maximum or minimum. That's just a change. It's just something else. So the procedure for doing these problems is you take the function and you find the critical numbers for this function, and then And it says here, find the critical numbers, find where the derivative is 0 undefined. That's how to find the critical numbers. Once you have the critical numbers, then you take the interval or the domain of the function, you break it up into intervals, which are defined by these critical numbers. And then you find out in those intervals whether the function's increasing or decreasing. So let's do this example. This is a third order polynomial. It could look something like this, or it could just go like that. We don't know. We don't know if it has a local maximum, local minimum, or if it just is continuously increasing. So to find the critical numbers, we take the first derivative. So the derivative of this polynomial, you're all good at that. So you get 3x squared 9 halves times 2x minus 12. So we can simplify that. We get that f prime of x is 3x squared plus 9x minus 12. And so what we want to do is find where the derivative is 0 and where it's undefined. Well, it's never undefined because the derivative of this polynomial is a polynomial. And polynomials are defined for all numbers, real numbers. So the only place we're going to have critical numbers is where the derivative is 0. So we set the equation for the first derivative equal to 0. Now, to find the values of x that are 0, we can go ahead and either factor out a 3 or we can divide by 3. I'm just going to say we're going to divide each term by 3. So this divided by 3 is 1, this divided by 3 is 3, this divided by 3 is negative 4. And I'm going to move this to the other side and factor it. And I chose the equation so this factors nicely. So you get negative 4 is 4 times 1 to get that, and we want a positive intermediate term. So we put the positive on the big one and the negative on the smaller one. So what that means is at x equals negative 4 and x equals 1, we have critical numbers. Okay, now we take those critical numbers and we use it to make a table up. And the table consists of 4 rows and in this case 4 columns. I'll explain how you get that in a second. So this is going to be interval, and this is to describe what's in this row. In this row we have the we're going to choose a value of x which is in each one of these intervals, and then we're going to evaluate the sign of the first derivative, and then we're going to write some kind of comment. So you can see I have 2 critical numbers. I need 3 intervals to define the entire domain, and I need 1 column for the headers, for the descriptors. So this goes from negative infinity to my more negative critical number, and then go from that critical number to the next critical number, and then go from that critical number to positive infinity. So this covers everything except the critical numbers. Then I pick values of x between these values, negative infinity, negative 5, 4. So I don't make it equal to negative 4, I make it equal to the next smallest integer in size. So I get negative 5 here. I'm going to go from negative 4 to 1, so 0 is always a good thing to choose. And a number between 1 and infinity, we'll choose the next integer. So then I go back to the equation for the derivative and evaluate the derivative at these x values, which are inside these intervals. So I do the first derivative of negative 5, so I get 3 times negative 5 squared plus 9 times negative 5 minus 12. Negative 5 squared is 25. 9 times negative 5 is negative 45. And so here I get 75 minus 45 minus 12, which is 30 minus 12 is 18. Now I really don't care what the value is, I just care if it's positive or negative. So I'm going to put positive positive there. Okay, f prime of 0 is going to be easy because I just plug 0 into here and I'll get negative 12. And that sign is negative. So that goes there. And not surprisingly, if I do f prime of 2, I'll get a positive number because it usually goes plus minus plus. So I get 3 times 2 squared plus 9 times 2 minus 12. So that's 2 times 4. 2 times 2 is 4. 2 squared is 4. 12. 12 plus 18 is 30. Is 30. Minus 12 is 18. So that's 18. Again, I just care that it's positive. Put the positive in there. And what those derivatives tell me is that the function is increasing in this first interval, then it's decreasing in the second interval, and then it's increasing in the third interval. So we look back here, which one of these two makes sense? Well, this is increasing, then decreasing, then increasing. So it's going to look something like that. If it was like this, we would have gotten increasing, increasing, increasing. So now those values of x are where we have a relative extrema. Now there's a rule that tells us whether they're minimums or maximums. You probably can figure it out just from looking at what we got there. We'll introduce the exact rule. You know, the easy way would just be to plot the function. But we want to use that table to make a decision. So the function looks something like this. May not be exact. Well, this one actually, yeah, it does have a minimum, maximum, minimum. It only has one x-intercept right here. But you'll notice that the maximum, this is a relative maximum. You go from increasing to decreasing. And that's true for this example, and it's true for every case. Likewise, if you go from decreasing to increasing, it's also going to be a minimum. So those are the first derivative tests. When a function goes from increasing to decreasing, like this, increasing to decreasing, you have a relative maximum. When a function goes from decreasing to increasing, you have relative minimum. That's the first derivative test. And so we could go back to this previous problem, and we can see we're going from increasing to decreasing. Therefore, at x equals negative 4, we have a local maximum. Here we go from decreasing to increasing, and therefore we have a local minimum. And you can kind of do that by drawing this increasing, decreasing, decreasing, increasing. You see that's a max, that's a minimum. So you can kind of remember it just graphically. Okay, so we will continue on and we'll do some more examples. For right now, we're stopping.